If a block sits on top of an inclined plane and there is no friction, what is the acceleration of the block as it slides down the incline? What is the acceleration if there is friction between the block and the incline? The first thing we need to do is to identify all of the relevant concepts. Now for this problem, we were given a situation where we may require friction. So we can label that as an F with a little sub F, so we have the force of friction. We also want to note that the concepts we are looking for involve an acceleration. So we have an acceleration, and we are also looking for two accelerations. And that would be with and without the force of friction. So the concept we're going to be using is Newton's second law, which is simply F equals ma. And this is going to be the sum of the forces in a particular direction that we're going to be looking at. Now we weren't given any explicit values to plug in, but we were given what we're looking for. We're looking for the acceleration with and the acceleration without friction. So let's go ahead and set up this problem. The first thing to do is to maybe create a diagram to make sure we have everything labeled correctly. So I'll go ahead and create this rather large so we can see what's happening. This will be our object, and we have a force pulling down, which is the weight. We were also given an angle. Now the easiest way to tackle this problem is to change our coordinate axis. So normally this is our y, and this direction here is our x. So that coordinate system is here as well. And in order to find our angles, we are basically going to rotate our coordinate system in this direction, perpendicular to the surface. So if you know, we increase our angle by that much, which is the same as moving this angle here. So this angle is the same as the one indicated on the incline. So now we need to resolve our red vector force here for our weight into two components, and it will be along this line like so, and this is 90 degrees. So this component here and this component here, this one will be the weight, and it's going to be cosine of that angle, and that's how you get that portion of the vector that makes up the weight. This one down here again will be the weight, except this time it's going to be sine of the angle. We also have a force from the friction, which is going to point opposite of the direction we're moving. So this here will be force of friction. So now that we labeled our forces in this diagram, let's go ahead and set up the rest of the problem in the execute step. Now if we were to start with the one without friction, so this will be without, and if we go back to our diagram, we make sure to note that when we drew our vectors here for our coordinate system, we are indicating the upward direction of the incline as the positive direction. So anything pointing in that direction is positive, anything pointing in the opposite is negative. So everything without friction, we have this sine component here that is pulling down, and we also have it equal to simply the mass and the acceleration that the entire system is moving at. So let's go ahead and set that up. We have the summation of all the forces in the x direction is equal to negative w sine theta. Remember, this is the force that's pulling down, and currently there's nothing slowing us, stopping us, or pulling us up. So those are all the forces. And this is going to equal the mass times the acceleration of the entire system. Now all we have to do is solve for our target variable, the ax. So ax equals a negative w sine theta divided by m. Now let's look at it with friction. Again, we're going to do the similar procedure that we just did. So the summation of the forces in the x direction equals, again, we have a negative w sine theta pulling us down, so that's why we're sliding down the ramp, But this time we also have friction. So we have a positive force of friction that's slowing us down. And that's going to equal the mass times the acceleration of the entire system. So now if we do a similar method and solve for a sub x, we will get f of f minus w sine theta, and all of this will be divided by the mass. Now let's go ahead and evaluate these answers to see if they make sense. Now we had, with friction, a force of friction minus the w sine theta, all over m. So let's disregard this m for now in our evaluation because they're similar to both problems. But if you think about it, if something is falling and there is nothing slowing it down, we'll have a larger value. And that's what we have over here, a negative w sine theta. On this left-hand side, when there is friction, we are slowing down some of that value. Now, the minus sign in front of the w here is only really indicating the direction. So the right side would have a larger negative value, and the left side would have a smaller negative value, which really indicates the magnitude of the speed.